In this video, I'm going to do a quick walkthrough of a very simple shell program. Of course, the shell program is the user mode program that implements the command line interface in all Unix and Linux systems. There are other more complicated shell programs, but this one is quite simple, and basically it does everything that a shell needs to do. It prints a prompt, reads a line from the standard input, parses it, building a tree representation, and then it executes that and loops back and repeats. The shell that I'm looking at comes from the XV6 operating system kernel. This is a very short and sweet kernel done by MIT for educational purposes. There's an implementation on the x86 architecture as well as the RISC-V architecture, and it's well worth taking a look at if you want to know more about kernels. So let's see what kinds of things the shell is capable of doing in its very short 400 lines of code. Well, you have a program name, and you can supply options that will be passed on to the program. You can do I/O redirection for standard in and standard output. You can pipe the output from one program into the input of another program. You can use the semicolon for program sequencing to run program 2 after program 1 completes, and so on. You can run programs in the background using the ampersand symbol. And finally, the parser recognizes parentheses, so you can do some grouping. There's also a single built-in command, the change directory command. There's a lot of stuff that's missing from this shell. No variables, substitution, or aliasing. You can use this shell program to run shell scripts, but there are no if or while loop constructs. There are a number of useful built-in commands that are missing. There's no line editing. The arrow keys and file name completion and so on is not present. There's no support for background control beyond the ampersand. The shells normally read in startup files when they first start executing, but that doesn't happen here. And finally, XV6 has no notion of environment variables, so those aren't supported by the shell. XV6 gets by with only about 20 system calls, and yet it really is truly a Unix system. The shell that we're looking at here only uses 11 system calls. For process control, it uses fork, exec, exit, and wait. For I/O, it uses open, close, read, and write. And for pipes, it uses pipe and the dupe system call. And finally, the change directory system call for changing the working directory. So let's take a quick example. And here we have a command line with some program sequencing and pipes and I/O redirection. And what happens is the shell will first parse this line and build a tree representation. And here I've suggested the tree representation. And then in a second pass, it will walk this tree and actually do this by executing the different programs as required, along with doing the file redirection and pipes and so on. So in this particular case, we have sequencing. So the shell program will create a child process to do everything in the parentheses here, and that's indicated with this dashed line. After that child process terminates, it will then go on to continue executing, and at that point will execute program 3. Within that child process, you see at the root a pipe. So the child process will create 2 child processes. So the first child process will be executing program 1, and the other child process will be executing program 2. The process that does the pipe will wait for both of those to finish, and then it will itself terminate, allowing program 3 to proceed. So the main functions that we've got here are parse command, which is a recursive descent parser, and run command, which will walk the tree recursively and execute the nodes. It will create child processes as necessary using the fork system call. So let's take a quick look at the nodes of the tree. Here I'm showing a struct like this. This struct has 3 fields, type, left, and right. And every node in the tree begins with a type field, which is an integer code. So there are integer codes for each of the different kinds of nodes in the tree, and pipe, for example, is node 3, or type code 3. It also has a left and a right pointer to the subtrees. For sequencing, you have a similar node called a list node with pointers to the left and right subtrees. For background operations, you've got a background node with a pointer to whatever is to be executed in the background, typically just a simple exec node. Now let's take a look at the exec node. The shell program takes an input line and reads it into a buffer. The buffer is of fixed size. It happens to be of size 100. And so it reads all the bytes into that buffer, and then it parses from that buffer and builds the tree nodes. And for this particular input, we see a program name and some command line options. There may be some other stuff on the command line, but for the exec node itself, we have only the program name and the options that apply to that program name. So the exec node has the type code as the first field, but then it has two arrays, argv and eargv. E, I suppose, stands for end. Each one of these will contain pointers into the buffer. argv sub 0 will point to the program name itself, or the file name containing the executable, and the remaining pointers will point to the options. The last one will be terminated with a 0. These are fixed size arrays, both of size 10, so we can accommodate one program name, 8 options, and then the terminating null. The eargv pointers point to the byte after the program name or after the option. After the parse, the shell will take a second walk of the tree and it will replace whatever character occurs in these positions with the null character. So after that, these pointers will point to null terminated strings, which can be used elsewhere. For the redirect node, we have the same sort of thing going on. The file pointer points to where in buffer the file name begins, and efile points to where in the buffer the file name ends. And when we do the recursive walk of the tree to replace these bytes with null, we will also replace this byte with the null character. So now file points to a null terminated file name. The redirect node will tell how we are to open this file. And so in this example, we are appending to the file if it already exists, so we want the write-only and create bits to be set. These will be passed to the open system call. The FD, or file descriptor field, will contain either a 0 or a 1 to indicate whether we are redirecting the input or the standard output. And finally, we have a pointer to whatever's to the left of this redirection. So this organization of the program is essentially this. We have a number of struct definitions, as we just showed on the previous slide. And for each one of these, we have a constructor function with the same name. Each constructor function is passed a few arguments, and all it does is allocate the node and fill in the fields and return a pointer to that node. The parsing is done by a function called parse command, which returns a pointer to the tree that it builds. There are some additional functions that are related to the recursive descent parsing. Null terminate is the function that recursively walks the tree and replaces those characters by null so that all the strings become null terminated strings. There's a function called getToken, which will read a token from the input buffer, or more precisely will identify where the next token occurs. Most of the action happens in the main function, and we also have a get command helper function which prints the prompt and reads in from standard input a line of characters to the buffer. And then we have the function run command, which walks the tree and executes according to whichever nodes it encounters. There are also two helper functions. Panic prints out an error message, and then it terminates the process. The shell program tends to create a fair number of processes. It creates at least one process for every command line that's entered. And we deal with errors in an interesting way by just simply printing a message and terminating the current process. So the shell itself exists in a parent process and will continue to execute. And finally, we have a fork1 helper function. This is a wrapper function for the fork system call that just checks to make sure there's no error when we invoke the fork system call. Now let's take a look at the code from MIT's XV6 project for the shell program. Here you can see the definitions of the 5 type codes. And after that, we see the structure definitions for the various kinds of nodes that I showed earlier. For example, the exec node has 3 fields, the type code and the 2 fixed size array, which are size 10. The other structures are similar, and here they are. For each one of these structures, there is a constructor function. So, for example, here's the constructor function for the pipe node. It takes pointers to the left subtree and the right subtree, and it allocates a node and sets it all to 0. I'm not sure this is necessary in this particular case because we then go on to set each one of the individual fields in the node. And then finally we return a pointer to the node. Now we can see that we are using a local variable command, which we end up returning here, which is a pointer to a pipe node. This thing in general returns a pointer to a command in general, but we have to typecast it here to get what we want. And it's similar for the other sorts of nodes. And in the case of the exec node, we see that the setting of the entire node to 0 is important because it zeroes out the 2 arrays. Okay, let's get into the main function, which is the most interesting part. The main function is pretty short. It goes from here down to here. But first, let's take a quick look at these helper functions, panic and fork1. Panic just prints the error message on the standard error using the fact that standard error will be file descriptor number 2. It's passed a pointer to an error message, it prints it out, and then it invokes the system call exit. Exit takes an exit code. 0 is considered success, while 1 is considered an error. So we've had an error message, we return 1. Fork1 is a wrapper for the fork system call. And basically it just calls fork and returns whatever that returns. However, it checks to see if there's an error. If fork had any kind of an error, then we print an error message instead and terminate the process. Okay, here's the main function. We've got the input buffer here, fixed size 100, and we see that we are getting a command, we're parsing it, and then we're running it, and that's occurring inside a while loop. First, let's look at the initialization here. Open is guaranteed to fill in any unused file descriptors. So the initial call to open will fill in file descriptor 0 and return that. So in this loop, we are opening files in a repetitive manner until we have opened something beyond file descriptor 2. So at that point, we close whatever we opened last, and we're done with the initialization. The while loop that does the bulk of the work reads in a command. The get command function is defined so that if end of file is encountered, it will return -1. So we're checking for that right here. And when we hit end of file, then the while loop terminates and the process itself, that is the shell itself, terminates. But assuming it's not end of file and we get something into the buffer, we first check to see whether the buffer contains a C followed by a D followed by a blank. And if so, that's the built-in change directory function. So if the change directory CD is used, then we make sure that what follows it is a null terminated string, so we replace the new line by a null. Buff plus 3 points to the character right after the plus, so we then invoke the change directory system call with a pointer to the file name. And then the continue here will cause us to repeat the loop. We'll skip this part down here. We have to do this in the shell because this change directory will affect what happens to the next time we iterate through this loop. If we did this in some child process, then it would have no effect on the parent, and that would be no good. We need it to be a permanent change to this process. Now, if it's not a cd command, then what happens? Well, we call fork. And remember, fork returns either 0 or a process ID. In the child process, fork returns the number 0, whereas in the parent process, it returns the process ID of the child. So the shell will call fork at this point, and at that point we will have a second process created. We'll have two almost identical processes. They will differ only in the value that fork returns. In one process, it will return 0. That's the child process. And in that process, it will go on to execute the parse command and the run command. And in the parent process, fork will return something besides 0. It will return the process ID of the child. So it will skip this, and instead it will wait. And it will wait for its child process to finish. So the parent will fork the child, which will do this, but the parent will then immediately begin waiting. And once the child is done and this child process terminates, the parent will continue. Run command will never return. Okay? Run command will terminate its process. So we don't have to worry about what happens to the child returning from run command. If there are any errors in the parsing or the running, then the child process will be terminated. With perhaps an error would happen and panic would be called, so we'd print an error message and terminate the process that way. Or perhaps the run command will run a program and everything will be fine and it will return success, but in any case that process will terminate and the run command will never return. Eventually the child process will terminate and the parent process will resume and then loop back to call get command, which prints the prompt and reads in a buffer from the input. Now let's look at the run command function. It's passed a pointer to the tree and it walks that tree, recursively calling itself. One key aspect of this function is that it never returns. It's executed in some process, of course, but it will finish by terminating that process. So we see some exits being called from here and there. The structure of the function is basically a large switch statement. So we see the switch happening here on the type code. And we have several cases for each of the various kinds of nodes we might encounter. Exec, redirect, list, pipe, and back. In all cases, after the switch statement ends, we'll exit. So run command will never return. So let's start with looking at the exec node. If that's what the root of the tree is, then we immediately typecast our argument into e command. There is a variable for each of the different kinds of nodes, and once it's typecast into e command, then we can access the fields of the node directly. arg0 is supposed to point to the null terminated string, which is the file name of the program we are to execute. All of the options are followed by a null pointer, and here we're just checking to make sure we have at least one item, which is the first one, which should be the program name. If there's a problem, we exit immediately. Otherwise, we do the system call exec. Exec takes two arguments. One is a pointer to a null terminated string, which is the file name of the program to be run, and the other is a pointer to an array, which is the argv array, which will be passed to the program. Exec will normally not return. So if it succeeds, it will not execute the print statement here. If there's a problem, for example, if the file name doesn't exist, or if it contains something that's not an executable file, then we'll print an error to standard error and then break the case and go to the end and exit here immediately. But if the exec works okay, then what it will do is it will replace the virtual address space of the process that invoked it with the code and data that are found in the file that's specified with this first argument here. So it will replace the entire address space with a new address space and then begin executing that program. Next, let's look at a redirect node. Okay, we start with a typecast, and the FD, or file descriptor field, in the node will either be 0 for standard in or 1 for standard out. And so whichever it is, we close that file descriptor and then we call open. The open system call is defined so that it will fill in or reuse the first unused file descriptor. So if we closed 0 for standard in, then this open will use file descriptor 0 and will return file descriptor 0. If we closed 1, then it will open file descriptor 1. The open system call has passed a pointer to the file name as well as the mode in which we want to open it. And if there's any problem, we print an error message and terminate. Otherwise, we call ourselves recursively. At this point, the file descriptors have been changed around a little bit, so run command will now run the program that is having its output redirected with new file descriptors. Next, let's look at the back node. This is for executing something in a background process with the ampersand. We have a fork here, and the process will create a child process. In the parent, fork returns the process ID of the child, which is not 0. In the child process, fork returns a 0. So the child process will go on to execute this, the run command. The parent process, however, will not. It will immediately break and then will terminate. That means the process itself will terminate. The child process will run on, but the process that invoked it will terminate, and this will allow the parent, which is waiting on this run command, to continue. And that's the main function. It will loop back and print another prompt immediately without waiting. Meanwhile, the child is a process that will run on its own independently and eventually complete. If we look at the list node, this is for the semicolon when we have program sequencing. It's very similar. We do a typecast and then we invoke fork. Fork creates a child. The child calls the run command on the left subtree. If fork returns non-zero, that's for the parent, then what the parent will do is skip this and it will immediately call wait. So it will wait for the child that was created here to terminate. Once that child terminates, it will then call run command and execute the right subtree. So now let's look at pipe. Pipe is probably the most interesting and most complex. So we see that the process that's executing the function here will call pipe, that's a system call, then it will call fork, and then it will call fork again, and then it will call wait twice. So each of these forks creates a child. This one creates the first child process, this one creates the second child process. So this code right here calls fork. The child process returns 0 from this system call, and so the first child will execute this code right here. Close, dupe, close, and the run command for the left subtree. The second child will execute the same, more or less the same thing. Close, dupe, close, and it will run the right subtree. The parent itself will first execute the pipe. Okay, I'll get to that in a second. but if that has a problem, it terminates right there. The parent will then go on to execute the fork. The parent will see that it is not returning 0, it's returning the process ID of the child, so the parent will not do this. It will then call fork a second time, and again, see that it's the parent, and then it will go on to close these two file descriptors, and then it will wait. It will wait for the two children to terminate. The first wait will wait for whichever child terminates first, either the first or the second. The second wait will wait for the other child to terminate. So after both children have terminated, this code will break and it will itself terminate. So now let's look at what pipe does. So the system call to pipe will create a pipe, which I've shown diagrammatically here, and it will open it, and it will assign P0 and P1. Going back to the beginning of the run command, we saw that there was a variable array here with two elements, P. And what the pipe command will do is it will fill in P0 with the next available file descriptor. Now, assuming standard in, standard out, and standard error open, that would be 3. And the other element of the array will be filled in with the following file descriptor, 3 and 4. 3 will be the file descriptor that essentially points to this end of the pipe, and 4 will be the file descriptor that essentially points to that end of the file. So after the pipe system call is made, this array here has been filled in with two file descriptors. Presumably there'll be 3 and 4. Okay? Now what happens here in the first child? Well, file descriptor 1 is the standard out. Okay, so we will close standard out, and then we call dupe. Okay, so let's imagine that we've got two programs, program 1 and program 2, with the standard out of program 1 is being piped to the standard in of program 2. Before anything happens, 0 and 1 are connected to the standard in and standard out, which is connected to the console or the asynchronous UART chip. In other words, it's where the terminal is connected to. So regardless of what these things are connected to before, what we're going to do is reconnect them. So let's follow this code a little bit more carefully. In the first child, which is going to be executing program 1, we close standard out, and then we call dupe. What dupe does, it's a system call which takes a file descriptor and it copies it. So in this case, P1 is 4. P1 is 4. It's pointing to the input side of the pipe. And the dupe is going to make a copy of that and put it into the first available file descriptor. Well, we've just closed file descriptor 1, so that's available. So what it's going to do is basically change file descriptor 1, and instead of pointing to the console, it's going to point to whatever 4 points to. So 4 points to this, so this will be redirected to point to that end of the pipe. So then we close P0 and P1, that is, we get rid of file descriptor 3 and 4, which aren't needed, and then we recursively call ourself to execute the left tree. So when we invoke run command, now we've got file descriptor 0, standard in, still connected to whatever it was connected to before, but now standard out, file descriptor 1, has been redirected to point to the input side of the pipe. The second child is similar. The second child will need to redirect its standard in to this side. So here we see that happening. We're closing file descriptor 0, so we're closing the standard in, and then we're making a duplicate of P0. Well, P0 is 3, so we're now causing file descriptor 0 to be a descriptor that points to the output end of the pipe. Again, we close file descriptor 3 and 4, which we don't need, and then recursively call ourselves to execute whatever to the right of the vertical bar. The parent continues along. Okay, it created the pipe, but it didn't do any of this stuff because it was the parent. Those were done in the children nodes, in the children processes. Instead, the parent will just go straight down here, close 3, close 4, and then it will wait on its children. So that, in essence, is how we redirect the input. So you can see now, when the child program 1 runs, file descriptor 1 no longer points to the console output. It now points to the input side of the pipe. So any write to standard out will not go to the console, but will go to this pipe. And likewise, child number 2, which is running program number 2, will have file descriptor 0 no longer pointing to the console device, but now pointing to the output end of the pipe. So program 1 writes the standard out, and that ends up being fed to the standard in for program 2. Pretty cool. Okay, we've gone over about half the code in the shell program. The remainder of the code deals with parsing and building the tree, and includes functions like getToken, parseCommand, and the null terminate function, as well as some others. I've broken that information out into a separate video, which I'm calling Shell Program More Detail, and you can check that out if you're interested. Well, that's all. Thanks for watching.